Hey everyone. All right, this is it. This is the day you've all been waiting for. We are finally going to start Galois theory. We're starting a new chapter. Its title actually is Galois theory. Before we get going on that though, I have I don't know if it's a confession or something like that. So the two chapters that we just completed, those were hard chapters, right? Chapters 3, normality, chapter 4, separability. The proofs are hard. I can't even say that I really enjoy those proofs. I think they're tough, right? And they're really detailed and intricate. Now, and here's what I really want to say is those two chapters, we had to get through them, right? We will need normality, we'll need separability, but they kind of give a false impression of what this class is about, right? I mean, this class is not about those intricate kind of details day in and day out, right? We're going to start doing the actual fun stuff, so to speak. So, hopefully those chapters and those proofs didn't scare you away or tune you, hopefully you haven't tuned out the class at this point. So and I guess that's enough, right? Let's we made it through the hard stuff. It's not that it's going to get easier, but it's going to get, in my opinion, more fun. All right, so enough said. Here we go. All right, so this is going to be chapter 5. So that's Galois theory. All right, so here we go. Given a field, let's say capital L, this is the usual thing. Let's let aught L denote the group of automorphisms of L. And what I mean by automorphism, it's a ring homomorphism from L to L that is both one-to-one and onto, right? So it's a bijection, or you can say it's an isomorphism, a ring isomorphism from L to L. Right? And so if you have a field, you can take the set of all such things and then under the operation of composition, right, it's easy to show that aught L actually is a group, right? So we've got the group of automorphisms of L. And maybe just under, in parentheses, right, the operation is, of course, composition. Okay, now, given a subset, so capital A of aught L, let's define capital, I don't know if that's a capital, I guess that's really a lowercase. Okay, sorry, define phi of A, and it's going to be equal to the set of all x in L, such that sigma of x is equal to x for all sigma in capital A. All right, so this is notation here. Phi of A will be the set of all elements of L that are fixed by every element of capital A. So now, okay, so let's just kind of think about this, and we're going to play around with this object right here. At this point, it's just a set. So now if x and y are in phi of A, and sigma is in A, then, so let's see, if we do sigma of x plus y, well, sigma is a homomorphism, so this is sigma of x plus sigma of y. Both x and y are in phi of A, so sigma of x is equal to x, sigma of y is equal to y, and so this is x plus y. Also, if we look at sigma of x times y, because we've got a homomorphism, this is sigma of x times sigma of y, which is equal to x times y. Also, sigma of x inverse, we know, is equal to sigma of x inverse, because we've got a homomorphism, and this is equal to, well, sigma of x is equal to x, so this gives us x inverse. So what did we just show? If we take x in and y in phi of a, then x plus y, x times y, and x inverse are all inside phi of a. They're fixed by sigma, all of the sigmas as well. And so what does that tell us? Okay, so it's closed under the operation of addition, multiplication, and all the inverses. Of course, this only makes sense when x is an invertible, is a unit, right? So as long as it's non-zero. And so what that tells us is, right, so conclusion is that phi of a is a subfield of capital L. And so this phi of a actually has a name. It's called the fixed field of A. Right, so phi of A is the fixed field of the set capital A. I remember when I was first teaching out of this book, the first time I used it, and they used this symbol phi. Why are they using phi? Oh, I get it. Fixed. Okay, so that's how I remember it now. So phi of A is the fixed field of capital A. Okay, so now I want to do an example, and this is going to be kind of a lengthy example. So we're just going to explore a little bit. So first, let's look at this. So let's say that tau is an automorphism of the rational numbers, right? So tau is an odd q. Okay, so first thing, we know that 1 has to be sent to 1. Okay, fine. So it follows that, okay, so if 1 has to go to 1, then tau of n, which is tau of n dot 1, where n dot 1 means 1 plus 1 plus 1 plus 1 n times, that's equal to n dot tau 1. But that's equal to n. Okay, so that tells us then that every integer has to go to itself, right? So the integers are fixed by tau. So then, as a consequence, if we look at a fraction tau of p over q, that's going to equal tau of p divided by tau of q, which is then equal to p over q. I mean, you could say I cheated here a little bit, right? It should really be tau of p times tau of 1 over q, but if you wade through the details, it's quick and easy to show that then tau p of q over q equals p over q. In other words, what does this say? If we take an automorphism of q, it has to send every element of q to itself. In other words, every automorphism of q, or the only automorphisms of q, is the identity mapping. Right, so conclusion is that ought q is trivial. at some point back in Math 481, I said at some point you stop writing E for the identity, and you then start using more advanced notation. If you're working in a multiplicative group, that's the symbol for the identity. If you're working in an additive group, that's the symbol used for the identity. So here, what we have is the conclusion is that ought Q is trivial. All right, the only automorphism of the rational numbers is the identity. Okay, so still I needed this to sort of set up the example. Now what I want to look at, so let's say now, let L, I want to look at an actual specific field here, Q adjoin square root of 2 and square root of 3. We've seen this, we've looked at this example before. We know that the degree of the extension L over Q equals 4, where their basis, right, for L as a vector space over Q, right, consists of 1, square root of 2, square root of 3, and square root of 6. Now, if we take sigma in L, then, well, let's see, sigma restricted to Q, right, has to be the identity, the trivial automorphism. And so, we saw this before, right? What this means is that sigma, every automorphism of L has to fix sigma. So we can say, and so, sigma fixes Q. And when we're considering an automorphism of an extension that happens to fix Q, then something good happens. This automorphism actually then behaves like a linear transformation from L to L. So as a consequence, sigma is well, I'll just say linear transformation, but it's an isomorphism, right? So it is a linear transformation of the Q vector space little l. Okay, so that's good because now we get to, and this is one of the amazing things that's happening here. I mean, notice I didn't really make a big deal out of it, but suddenly we're talking about group theory. Right? We've been talking about fields this entire time. Suddenly we're talking about group theory, and also we're bringing in some linear algebra. And so we get to use the power of linear algebra, and my goal is to make sense of that right there, L. Okay, so let's think about linear transformations now. Well, linear transformations are completely determined by what they do to a basis. Right? Thus, sigma is completely determined by its effect on the basis. So if we know what sigma does to 1, root 2, root 3, and root 6, then we're done. We know everything about this, this automorphism. And this is the great thing. We get to any time if we have an automorphism of a field that, or let's say, right, let me point down here. So if we've got an extension L over K, right? Remember this. Anytime if we have an automorphism of L that fixes K, then that automorphism behaves like a linear transformation. And so then we get to say, okay, we know something about linear transformations. They are determined by the effect on a basis. So, all right, fine. We have sigma of 1, of course. 1 is a rational number, so it's got to be 1. Also, sigma of root 6, that's equal to sigma of root 2 times sigma of root 3. So what that tells us then is if we know what sigma of root 2 is and we know what sigma of root 3 is, then we know everything we need to know about sigma. So we can say, and so sigma is completely determined by sigma of root 2 and sigma of root 3. If we can specify what sigma does to those two elements right there, then we can tell you what sigma does to any element of Q adjoint root 2 and root 3. Okay, so now what we need to know is what are our options? What possibilities are there for sigma of root 2 and what possibilities are there for sigma of root 3? Can we send them anywhere or do we have some kind of restrictions? So let's think about that. So let's say if sigma of root 2, let's just call it, I don't know what it's going to be, let's call it alpha, is some element of L. Then when we look at alpha squared minus 2, that's equal to sigma of root 2 squared minus 2, which is, that's sigma. So we've got a homomorphism here, so I can bring that 2 inside. That's sigma of 2 minus 2. But 2 is a rational number. Sigma has to fix it. So this is equal to 2 minus 2, which is equal to 0. In other words, what is that telling us? We are extremely restricted on where we can send square root of 2. It has to go to a root of the polynomial x squared minus 2. In other words, sigma of root 2 can only be positive root 2 or negative root 2. Thus, alpha is equal to plus or minus square root of 2. And then basically the same argument tells us that sigma of root 3 can only be positive root 3 or negative root 3. So similarly, sigma of square root 3 has to equal plus or minus root 3. And of course, what you might be thinking here, the minimal polynomial of square root of 2 is x squared minus 2, and so root 2 has to go to a root of its minimal polynomial. Same thing with square root of 3, right? And that'll be our more general idea. Remember all those extension theorems we studied where we had alpha going to beta, right? It all involved minimal polynomials. Right, so all that will come back into play in a little while. Okay, so now, so I'm trying to make sense of what kind of automorphisms do we have? Who are the automorphisms of L? Right, so it goes like this then. Thus, we have 4 choices for automorphisms of capital L. right? So square root of 2 will go to either plus or minus, positive root 2 or negative root 2. Same thing with square root of 3. Once we've determined that, that completely determines everything else about sigma. So, and I want to give these names. So first of all, let's write it over here now. So what this is saying here is that L has exactly 4 elements in it, right? As a group, it's a group of order 4. And let's write down who the elements are. We're going to give them names. So the first one is the identity, right? That's the one that sends positive root 2 to positive root 2 and negative and positive root 3 to positive root 3. So root 2 goes to root 2 and root 3 goes to root 3. If that happens, then everybody goes to itself. It's the identity mapping. Then there is, let's call it sigma, and that's going to be the one that takes root 2 to negative root 2, and it takes root 3 to itself. Right? So there's another automorphism. There's another one, let's call it tau. That takes root 2 to itself and takes root 3 to its negative. And then the last one would be the one that takes root 2 to negative root 2 and root 3 to negative root 3. And notice that's actually just the composition, sigma of tau. And so we also have sigma tau. That takes root 2 to negative root 2 and root 3 to negative root 3. Okay, so those are the 4 elements. And you can check well, how do I want to say this? So let's say it like this. So note, or we have, right? Say it like this. So L is a group of order 4, and so what do we know about groups of order 4? Well, L either has to be, so it's isomorphic to Z4 or Z2 plus Z2, right? Every group of order 4 is it's either the cyclic one or the non-cyclic one. So those are our 2 options. Okay, so then the question is, which one do we have here? Got a group of order 4. Well, let's look at the behavior of these elements right here, and you can check that sigma, tau, and sigma times tau all have order 2. So let's just say check that the order of sigma equals 2, the order of tau equals 2, the order of sigma tau equals 2. I mean, it's pretty obvious, right? If you send root 2 to root 2 and then do that, root 2 to negative root 2, and then repeat that, that's going to send root 2 to negative root 2, which goes to positive root 2 as you iterate it. And so that sends root 2 to itself. That's how you get the identity. In other words, there's no element of order 4 in L, which means that L has to be isomorphic to Z2 plus Z2. So therefore, L isomorphic to Z2 plus Z2. Okay, and we're still working on this example, and I want to continue. Because remember, we talked about fixed fields, and how did that work? If you take a subset of L, capital A is what we were calling it, we could then ask who is the fixed field. Now, in most cases, we're not going to be caring about the fixed field of a subset of L. We'll care about a subgroup. And so let's look at the fixed fields. So first, we can look at phi of 1. All right, 1, the trivial subgroup. Now, okay, so what elements of L are fixed by every element of the trivial subgroup? Well, everybody is fixed by the identity, so the fixed field of the trivial subgroup is equal to L. So now let's look at, so now we want to look at the fixed field of the subgroup generated by sigma. So let's kind of bullet point this. There's our first one. So now let's consider the fixed field of the cyclic subgroup generated by sigma. All right, so what would this mean? Well, this is going to be the set of all x in L such that sigma of x equals x. For a technical guy, I have to say for all sigma in this group, but of course it's just the identity and sigma, so I can close it off right there. Okay, so let's see who it is. Let's see which elements are fixed. Okay, so how would we do that? Well, let's write x equal to, so it would be something like a plus b square root of 2 plus c square root of 3 plus d square root of 6. I'm writing an element, it's just a generic element. We can express it as a linear combination of our bases. So then, sigma of x, okay, so how will that work? It'll be a minus b root 2 plus c root 3 minus d root 6, just using the formula for sigma. And we need this to match this. All right, if you're going to live in the fixed field, well, what would that tell us? So for sigma of x equal x, we would need b root 2 to equal negative b root 2. So we need b root 2 equal to minus b root 2. Also, we would need d root 6 equal to minus d root 6. So, and d root 6 equal to minus d root 6. Now, how is that possible? Well, that would mean that b has to equal 0 and d has to equal 0. So we can say this occurs only when b equals d equals 0. Okay, so this completely characterizes the elements that live in the fixed field of the cyclic subgroup generated by sigma, right? They're the ones for which the this part is gone and that part is gone. In other words, they're the elements of the form a plus c root 3. Okay. So the fixed field of the subgroup generated by sigma is equal to the set of all elements of the form a plus c root 3, where a and c are elements of Q. And we have a nice symbol for this, right? This is exactly Q adjoin square root of 3. And you can go through this for the other ones, right? So similarly, Q adjoin square root of 2. Let's say it's better. Sorry. The fixed field, I want to identify fixed fields, right? So similarly, The fixed field of the subgroup generated by square root of 3 is equal to Q adjoin square root of 2. And the fixed field of the cyclic subgroup generated by, oh, what am I doing? Sorry. Why did I write a square root of 3 here? This should be tau. And then the last one would be the subgroup generated by sigma tau. Yeah, so that's equal to Q adjoin square root of 6. Anybody else? Any other subsets? Oh, I mean, who's fixed by? We could take this one more step. Who's fixed by every single automorphism? Well, that's just going to be, who's that going to be? The fixed field. Who's fixed by everybody? Oh, you know what? I don't even want to write this down. Never mind. I don't want this. Sorry. Do I? Oh, actually, I kind of want to think about this for a second. So let's see. What would you have to look like? Oh, of course. Who are you going to be? It's going to be Q. Duh. Sorry. Sorry, I spaced out there for a second. Okay, so as at the beginning, I was saying something like, we had to kind of fight through some hard stuff, and now we're now we're going to really start, having fun, right? We're going to see how all of this stuff comes together, right? We got groups coming into play. We've got linear transformations coming into play. How are we doing on time here? Let me just say a little bit more. So far, here's what we have, just to kind of recap. So far, for each subset, although in our case it's going to be almost always each subgroup of aught L, but it makes sense, you can say it for any subset. So for each subset of aught L, there is a subfield phi of A. And so what this does then is it induces an extension, right? So thus for each A in aught L, there is an extension L over 5A, right? We know that 5A is a subfield of L. Okay, so now, so what do we have? For each subset of aught L, we have an extension, a corresponding extension. And now we're going to kind of work in the reverse direction now. So now let's say that we have an extension. So given, all right, so sort of change of directions here. So given an extension L over K, what I'd like to do is I'm going to define, so let's define it up here. So define gamma of L over K. And it's going to be the set, I'm going to use sigma, set of all sigma in aught L, right? So the set of automorphisms of L such that sigma of, well, let's use x, I guess, sigma of x equals x for all x in capital K. So it's the set of automorphisms of L that fix K. All right. In fact, let's say that in words. So that is gamma of L over K is the set of automorphisms of L that fix K. So now let's take a couple of elements in there. So let's let, say, sigma and tau be elements of gamma LK. And let's take somebody in K. So let's say a little x in capital K. So then, if we look at sigma tau of little x, remember this is composition, so this means sigma of tau x. But tau, because it lives in here, it fixes x. So this is equal to sigma of x, which is equal to x. Also, I would say and sigma inverse of x is equal to sigma of x inverse. Let's say that right. Oh, you know what? Let me say this a little bit smarter here. Okay. Yeah, I don't want to do that. I want to do it like this. So we know that sigma inverse of x is equal to sigma inverse of sigma of x. All right, why is that? Because sigma of x is equal to x. And then this is equal to x. Thus, sigma tau and sigma inverse are elements of gamma of L. Oops, I put a comma there. It should be a colon. L over K. So what did we just do there? Sigma of LK is a subset of L. And we just showed that it's closed under multiplication and inverse. In other words, we just did the subgroup test. So we can say, therefore, gamma of L over K is a subgroup of L. In particular, the important part here, it's a group. So what does that say now? Right, a minute ago we were saying every time you take a subset of L, it induces an extension. And now in the reverse, every time we have an extension, it induces a group, a subgroup of L. So each extension, L over K, induces a group, gamma, of L over K. So what do we have now, right? And yes, I know we did this capital A subset of L. All right, and then we did phi of A. In particular then, if we insist that A instead is a subgroup of L, then still we get this fixed field. And then the fixed field corresponds to an extension L over phi of A. So every time we have a subgroup of L, we get an extension L over phi of A. On the other hand, every time we have an extension, we get a subgroup of L. Right? So we've got this sort of back and forth interplay between fixed fields and these subgroups of L. And so we're going to end it right here with a formal definition. So the group gamma of L over K, this has a name, so this is the Galois group of the extension L over K. So this is the genius of Galois. This is the amazing part about this theory, right? Every time we have an extension, if we want to study extensions, it gives us this corresponding group that we can study, right? This gamma of LK. Okay, so that's a good place to stop. We will see you next time.